For this video, we are going to look at tree diagrams. Now, making a tree diagram is a very cool visual way of representing your sample space. It's also a great way to see if things are dependent or independent based on previous polls or trials. Now, the first thing I'm going to do is use an example from going out to dinner. Now, sometimes when you go out to dinner, they offer you a package price. That is maybe a dinner special for two, or maybe a combo during lunch that will offer you a smaller array of choices for a better price. The way that the restaurant can make money by this is making sure that the items that are offered are high in caloric intake or high in satisfaction but low in cost. So, for example, endless breadsticks or free chips or something like that. So with this problem, you get to basically get the dinner package, and you're only given 2 appetizers. Now, how you start a tree diagram is that you create a starting point, and that starting point is you making the choice. And I said that you could only have 2 appetizer choices, so that would be appetizer 1 and appetizer 2. Once you make your appetizer choice, then you get, let's just assume, 3 entrees. So these are your main courses. Like maybe these are, a salad option here. Maybe this is some hamburger option. And over here, maybe some kind of cool quesadilla option. So there you have your option 1, 2, 3. And here you have, if you chose this appetizer, the same options 1, 2, and 3. This is an example of an independent choice, because what you chose for your appetizer does not affect your entree choice. Then they usually offer some kind of dessert, and we're going to make it simple by only offering 2 options for dessert. So I'll have my D subscript 1 and D subscript 2 indicate the dessert options. So if I follow this path, which is appetizer 1, entree 1, and dessert 1, this is one possibility you could have chosen. You could have also chosen appetizer 1, entree 1, dessert 2. So every completed path represents one outcome in your sample space. And these were all independent choices because picking one did not affect the pick of the other. The restaurants would just have lots of these on hand and probably would know ahead of time which of these choices were more popular than the other to kind of accommodate for that. So what this gives you is 2 options here, 3 options on this row, and then 2 options on this row. So with 2 appetizers to choose from, 3 entrees to choose from, and then 2 desserts to choose from, you can multiply these together because these were independent. So 2 times 3 times 2, that's going to make 12 different paths that you can take from going from the top here to the very bottom. Now we're going to do so with now flipping 3 coins. Now you can also think of this as flipping the same coin 3 times, which is probably a little bit easier to think of it as one flip at a time rather than 3 coins being flipped in the air at the same time. So you can see that we're going to have heads or tails for the first flip of the coin. So that's 2 possible outcomes. Then after you flip the coin once, you'll flip it again and you can get heads, tails, heads, tails. Now in a previous video, we actually flipped a coin 2 times and showed you that there were 4 possible results. Heads, 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 tails, tails, heads, tails, tails. Or 2 times 2 makes 4. Now a common question on tests and maybe college placement exams is, if you flip a coin 3 times, how many total possibilities are there in your sample space? Or something to that effect. Most people would guess 6 because they're wrong, because they go 2 times 3. But in fact, the answer is 8. And the reason why the answer is 8 is because if you have another pair of independent choices here, whoops, that should be a T, not an H. Erase that there. Okay. And put the T there. Here's heads, tails. So now what you have is 8 possible branches. Heads, 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 tails. Heads, tails, heads, heads, tails, tails. Tails, heads, heads, tails, heads, tails. Tails, tails, heads, tails, tails, tails. So 2 times 2 times 2 is 8. Not 6. which is a common mistake because we had two choices at each row. Now we're going to get to one of my favorite games on The Price is Right, which is called the Safecrackers game. The Safecrackers game was for a pretty good price, usually some trip or some very high-end appliance, usually between $3,000 to $7,000. But what you had to do in the Safecrackers game is you had to actually bid on a lower cost item and get the price right to win the big prize. So they would cart out this beautiful dishwasher, and they would say, okay, you have to guess the combination of the safe, which just happens to be the manufacturer's retail price for the dishwasher. So there are three numbers in the price of the dishwasher. There's a 0, a 9, and a 5. So you have to make a choice to what the first number of the price would be. Would it be a 0, a 5, or a 9? Now, if you choose the 0, and this is kind of the cool trick of the Safecrackers game, it is known, because they tell you the rules of the game, that you can't use the same number twice. So, whereas in the heads and tails, flipping a head wouldn't mean that heads or tails were taken off the table. The numbers get taken off the table here. So you have three choices, but then if you choose the 0 first, because you think that's a cheap dishwasher, then the next number you can pick is either a 5 or a 9. And then after that, once you pick the 0 and the 5 for the first and second spin on the Safecracker wheel, then the last one would be a 9. So you think it would be a $59 dishwasher, which is ridiculous. But if you chose the 0 and the 9, then that would be $95. Okay? So, a better choice would be choosing either the $500 or the $900 dishwasher. So if you choose the 5, you can either choose 0 or 9 after that. And then after that, you only have one choice. You're pretty much only making two choices, and then the third choice is locked in. Whoops, that should be a 0. All right, so probably this is a $950 dishwasher. $905 could be a possibility, but most prices end, with a 9 at the end or a 0 if you look at manufacturer retail pricing. So that is the Safecracker game, and you'll notice that we had three choices at the first row, and then you had two choices in the second row once you picked your first number, and then you had one choice in your last row, because once you pick your first two numbers, you only have one path to go. There are 6 ways to do this game, and in fact, when you kind of think of this example here, there's really only 4 that would make somewhat sense in the Price is Right context. So this is a game that often gets won on the Price is Right because people yell and scream if they see you picking a bad number, and most likely the audience is going to kind of steer you in the right direction. So tree diagrams allow for pretty cool counting rules because you can see all the total possibilities. Now, in the next example, we're going to go a step beyond just counting possibilities, and we're going to get into counting probabilities. Now, the reason why we here talked about possibilities is each of these, if chosen randomly, could have happened as random as the other choice. If you just basically went in and just say, well, I'll just pick, randomly picking things to eat, or if the coins are the definition of random. And the Safecracker game could be random if you just spun the wheels, much to the chagrin of the audience. So let's go to the next part, where we're going to deal with drawing cards. Now, there are 52 cards in a deck, but what we're going to do is we're going to make this a little easier on us. We're going to break the cards into 2 different categories. We're going to talk about face cards and non-face cards. And by breaking these into 2 categories, face cards and non-face cards, then we can make very simple tree diagrams that will also have very computable probabilities. You're going to want your calculator for this one too. So, drawing 2 cards with replacements. And again, our sample space has been restricted to face and non-face cards. So what we want to do is just kind of look at the probabilities of drawing 2 face cards or non-face cards with replacement, which means that we're going to put the card back every pull, and then we're going to take a look at pulling 2 cards without replacement. So we're going to kind of cut this in half, and so what we're going to answer are problems 20 and 21 for each of these possibilities here. So, drawing two cards with replacements. We're going to start off with you, and again, we're looking at either drawing a face card or a non-face card. So I'll just draw a line through the letter F, which stands for non-face. You also could use NF for not face. Now, there are 12 out of 52 cards that are face cards. There are 4 jacks, 4 kings, and 4 queens. And there are 4 of each because of the 4 suits in a deck of cards. That would be heart, club, spade, diamond. Now, the complement of face is no face, so that would be 40 out of 52, because the complement of F and F prime, F prime, I'll do that on the next one, is 40 out of 52. Both of them together would make a full deck. Now, we're going to try to draw either a face or a no face card here, and the face card would then be the same as this probability, because when we draw the card, we're going to put it back in the deck. And then this is going to be 40 out of 52, because, again, putting the card back in the deck is going to keep that the same. So here we go, face, no face. And then we have, again, 12 out of 52 and 40 out of 52. All right, let's see the question here. The probability of picking 2 face cards in a row. Okay, 2 face cards in a row is going to be this path. This is 1252 and 1252. So since these are independent events, since we put the card back in the deck, we are going to use our calculator for this. So let's go use the technology, and we're going to go with, click the on button, that would help. I like to type this in like a good parenthesis with the parenthesis, or a good fraction with the parenthesis key. And since we're using multiplication, you can type the multiply sign or just use another parenthesis. The calculator will default into that. And so our answer for this is going to be blam, about 5.3%. Now if I clicked on math and I clicked on 1 or enter, I can convert that into a fraction. So 9 out of 169, or 5.3%. So let's write that down. 9/169, or 5.3%. Hold on a moment. Okay. Now, let's go and compare and contrast that. Oh, let's do this one first. Okay, picking 2 non-face cards in a row. 2 non-face cards in a row. Okay, so picking 2 non-face. Well, it wouldn't be this path, right? Picking 2 non-face cards in a row wouldn't be this path. It wouldn't be this path either, because these 3 paths down these arrows, you can see that each one of these has at least a face card. So picking 2 face cards in a row would be this path, the 40 over 52 and the 40 over 52. So I'll get my calculator back here. Now, I'd like to go back and change these to 40s. So if I hit second enter, it brings back my last input, and I'll do second enter again. And now what I can do is just back up the cursor here and type in, instead of the 12, I can type it over the 40. This is really nice to save you a little bit of time. Okay, so that looked like it's going to be about 59.2%, or if I click the math button and click the 1 button or the enter button, and then enter one more time, now I have my fraction, 100 over 169, or 59.2%. So, looks like my answer is 100 over 169, or 59.2%. So you can see that the chances of you getting 2 aces, 2 kings, 2 queens is going to be a lot less likely than getting 2 face cards in a row, which is important to know in Texas Hold'em. So now let's do the same thing with 2 cards without replacement. So we're going to start off with drawing a card out of the deck. So here we have a face, which is 12 over 52, and here we have no face. So this is the complement of F, which is not face, which is going to be all our 8, it's our ace, 2, 3, 4, 5, 6, 7, 8, 9 of all the different suits. So that's going to make 40. I just wrote 12. 40 out of 52. Okay, so let's say I draw a face card. Now I'm keeping that face card and let's say I draw another face card. Well, that means I had 11 face cards left in the deck out of 51. So that's important because you can see that it changed the numerator and the denominator. But what if I draw a face card first and then not draw a face card? Well, there were 40 of them in the deck, but there were only 51 cards in the deck if I went down this path. Now, if I go down this path, this is drawing a face, a no face, then face. Then there were 12 face cards, but 51 cards in the deck. But if I go no face, then there were 39 cards in the deck and 51 cards in the deck. So you can see without replacement, it becomes a dependent event. But since we have adjusted our fractions accordingly, we can still use our multiplication rule for this. So let us use the multiplication rule to figure out picking 2 face cards in a row. So this would be, whoops, just make sure I got my pen ready. Come on, pen. There we go. So this is the probability of picking a face and then picking a face. That's a comma there. And this would be picking a no face and no face. All right, so picking a face and a face. So what we're going to have here is 12 50 seconds multiplied by 11 50 seconds. All right, so let's get to a let's get to the calculator here, move it over here to be a little easier for us. Okay, so second enter, get that old equation back here, and I'm going to type in 12 50 seconds and then type in 11 51sts. Just changing the numbers here and then hitting enter. And there's my percentage chance. You see it's actually lower than the with replacement because I'm actually have fewer cards to grab once I pull one of them out. I'm going to go math fraction, and it's 11 over 221. So it's now this, in terms of rounding, this would be rounded to 5% because the 7 pushes the 9 to a 0 and pushes this one. So it's 5% or 11 221sts. So the answer to this is 11 221sts or 5%. What's cool is you can compare that to this, and without replacements, much harder than with replacement. And so that would assume that I would assume this 59.2% to be greater than this answer. So let's check it with the technology. So we're going to go second enter, and change our numerators here. So the first numerator is a 40 because we had non-face cards, and the second numerator is a 39. So you can see that 58.8% is definitely lower than 59.2%. And as a fraction, even though the fraction itself has smaller numbers, 10 over 17, 10 17ths, if I multiply top and bottom by 10, would be 100 over 170. So 100 over 170, you can see, is a smaller fraction, because the bigger the denominator, the smaller the fraction, than 100 over 169. That's a little bit kind of some nice advanced math to think about right there, how the bigger the denominator, the smaller the fraction is. We'll think about like 1/2 versus 1/4. 1/4 is a much smaller portion of the pizza than 1/2. As long as the numerators are the same, you can compare the denominators for size. Hey, number sense. That's what the young kids are learning today. So we have this situation here where we had our fraction of 10 17ths, which is comparable to 100 over 170ths, and our percentage is going to be 58.8%. All right, so for our final example, we'll get to talk about my favorite thing, kittens. I really do enjoy, I'm definitely a cat person, although I do love dogs, but I'm more of I'd like rent a dog if you could, like, you know, send a dog to my house in the morning, and I play with the dog for all the day, and the dog doesn't have any work to do, you know, so I like the dog without the work. But I'm totally a cat person. I will overlook a lot of cat problems to have one. So here we are. We're going to adopt 2 kittens. Now, let's set up the situation here. These 2 kittens come from a litter of 9 cats, okay? And there are 2 different styles of cats. There are tabby cats, and also my favorite, black cats. I'm definitely a lover of the Halloween kitties. So let's go and kind of set this up with adopting 2 kittens, and let's just assume we do it at random. Because let's just assume personalities are random, and we're going to enjoy 2 of the best cats with the best personalities. So here we have just you. I'm going to move over here. Just gives me a little more room. So you get to either pick the tabby or the black kitten. The tabby, there are 4 of them, and the black tabby, there are 5 of them. So your chances of picking one randomly is either 4 nights for the tabby or 5 nights for the black kitty. Now, you're picking a second one. Why don't you try to write this in? Pause the video if you'd like. Write this in and write the correct fractions, because this is a dependent event which needs some fraction manipulation, because once you pick a cat, you can't pick the same cat again. You're taking home 2. So the first easy part is you're picking either another tabby or another black cat. You can put little numbers under here if you wanted to. But if you pick a tabby and you pick another tabby, well, there were only 3 to choose from out of the 8 in the litter. If you pick a black cat, all 5 cats were there after you pick the tabby, but there were only 8 cats left. Okay, what about this path? Well, then this would be 4 tabbies out of 8. And then here, if you pick another black cat, this would be 4 out of 8 as well. Aww. All right, so now, what are the chances that both kittens are black? Okay, so if you want to compute this, and I think what I'm going to do is I'm going to actually have, I'm going to write these out and then do all the computations on the calculator so we can see them. Okay, so what we have, both kittens are black. Well, the first chance was 5 ninths, and then we use our multiplication rule, and our second chance was 4 eighths. Okay? All right, so some of you might be feeling like, well, when do we do the addition symbol? We use the addition symbol when we have an or situation, like one or the other could happen. We're actually going to see that on this page. But this is the only path where both kittens are black, and when I compute this out, it's going to give me a fraction, and it's going to give me a percentage. Now, what are the probabilities of getting one of each color? Now, what that means is that you can travel down this path of tabby black. So I'm going to put a little yellow symbol there. You could also pick this black cat and then a tabby cat. I'll put this little symbol here. So the yellow indicates the one of each color. So in the first path, we would have 4 ninths times 5 eighths. And in the second yellow path, we would have 5 ninths times 4 eighths. Now, you would multiply these together and then add them together. So this is going to take a little bit of calculator work when we do this, and that's why I want to kind of keep the calculator work separate from the logic here. This gets a plus because it could be either the left yellow path or the right yellow path. And since we have an OR situation, because these are 2 ways to get one of each color, then you'd have to add up these probabilities once you figure them out. And again, we will do that. On the calculator at the end. Now, what are the chances of getting 2 kittens of the same color? Getting 2 kittens of the same color, well, we're going to think about a green path. So if we follow the tabby, it would lead us to this place at the bottom of our path. Or we could choose the 2 black kittens, and that would give us, look at this, the green path here. So just like the one above it, we would have 2 probabilities added together. So 4 ninths times 3 eighths plus 5 ninths times 4 eighths. All right, so to finish this video, let's just show you how to do this on the technology. All right, move this over here. Now the first one's very straightforward. Let's go hit the on button, clear out our calculator for 5 ninths, written as a beautiful parentheses problem times 4 eighths. Okay, bam, there you go. 27%, and if we want to turn that into a fraction, 5/18. So let's write that down. 5/18 or 27.8%. Again, if XYZ homework tells you to enter it in as a decimal, you will do so without moving the decimal, and please just watch the rounding rules there in the XYZ homework. Okay, so let's do this more challenging problem. One of each color. Okay, so for this case, what I'm going to do is I'm going to do this in two phases on my graphing calculator. I'm going to go parentheses 4/9, okay, times 5/8. Okay, 4/9 times 5/8. Now I'm going to hit enter. Now before I do anything with that, I am going to then hit plus. So this is like I'm right here in the middle of the equation. I've taken that 4/9 times 5/8 and I'm going to add to it parentheses 5/9. Whoops, I forgot my division key. 5/9 times 4/8. Now what's great about the graphing calculator is it's going to do order of operations correctly. It's going to do all of these parentheses and multiplication before it does the addition to that. So this is going to give me an answer of around 55% here, which is pretty sweet. And I am going to now go and convert this. So I'm going to go with my math key and I'm going to go to my fraction and give it the fraction of 5/9. So this is 5/9 and 0.55555, so on and so forth. So if I move the decimal 2 over, it's 55.6%. So that's 4/9 times 5/8 plus 5/9 times 4/8 to give me this answer, and let's go write that down. Okay, so we now have an answer of 5/9, which is 0.55555 repeating, so 55.6%. Two kittens of the same color. Now, there's a couple smarties right now who can guess the right answer without typing anything in. Now, I will show you how to type this in the long way, but again, if you think you've got a super shortcut technique to use right here, go for it. Go for it. Try to do that and figure out like what would be the answer of following the green path to get these two answers. Okay, I'll let you try that. Did you figure out the trick? And if you didn't figure out the trick, that's fine, because sometimes brute force is just fine. So let's go with 4/9 times 3/8. So 4/9 times 3/8, and so I'm going to hit second enter, second enter. I'm going to do this a couple times because that'll get me back to here. 4/9 times 3/8, okay? Then I'm going to go plus, and that way I can hit second enter, and get back that plus with the thing I needed. Okay, and then 5/9 times 4/8. Hey, 0.4 repeating. And if I math frac that, math 1, blam, 4/9. 4/9. Did some of you figure this out a little bit? Because if you compare the green and the yellow, notice they're complements of each other. And complements always add up to 100%. So if you had 5/9 here, you'd have 4/9 here, or 44.4% if you add that to the percent above it. It'd be 100%. Wow. Complements. So great to know about and look for these cool side hacks or tricks here. Well, thanks for watching this informative video about tree diagrams and how we can use tree diagrams for counting methods and probability methods. Thanks for watching.